start when they're like this, when you run it like.
Kinder, you wasting your time. You did not start your video yet. Can I'm almost done.
I'm almost done with my task. Yeah, Mama.
Wait,
Look at my picture here. It should be right at Miss Gozer's.
Mom, I'm gonna stay with you forever.
Yeah, it should be schedule for the week. Look like this, the little blue thing. If you click onto that, it should load. So here's the chat button. How Dulce gets in every morning, and then right next to it is what we want you to click on.
There's sometimes. There's sometimes you look at the time.
But if it's too much for things to go on,
Yeah, me too. Sometimes, when it's almost 12 o'clock, that means we're almost done, right?
Then I know I'm working on an addition number sentence. So here is my plus sign.
1, 2, 3. It's gonna take like 2 hours.
Tina, does she mean this one?
Girl has a brother.
No, it's the
That one is
video.
called 3 stars.
Mama, what is this? Did you ate it and Tina? No, that was just Mama chocolate, and I just only ate one bite. Mama said if we're done talking to our sister and done with everything, we're gonna have that chocolate. It's so.
I did get your extra credit for the hyperbolic geometry.
Okay.
I felt it was nice, so I was just looking into it, but I'm a little confused, so I'm not graded you as I have graded everyone else. So
Okay.
give me a few more
Yeah, no problem.
days, maybe. Nothing significant, it's just I want to comment something.
Yeah.
But it's good work and whatever. Like, I'm not sure whether they really intersect or not, so I want to check that.
Okay.
Like you drew the square with the
Square.
hyperbolas intersecting.
Yeah.
I suspect that they don't intersect.
Okay, I was confused about that too.
Yeah. So I want to check on that. Don't want to say that you're wrong. Before that, I wanted to at least a little bit, if I have a feel for it.
Yeah, that's why I stopped there because.
Hi.
Oh, hello. Nice. How are you? Don't you have any school?
Yeah, we have school FaceTiming our teacher and a computer. Yeah.
Hey, how is it going?
Good.
Hey, good.
I'm 6 years old and he's 7 years old. Yeah, I'm 7.
Okay, how do you know?
Good.
No, how do you know that you're 6-year-old?
Because It was our birthday and we ate a cake. Yeah, it was our birthday last year ago. And we ate a cake. Last year I was 5 years old, but now I turned to 6.
Very good. Very good. Okay. Does Mama disturb you when you are doing your online classes?
What does that mean? No.
Yeah, so you should also not disturb Mama when she's taking the class, right? But it's nice seeing you guys.
Thank you.
Yeah,
Thank you.
you're welcome.
2 of my teeth fall off. And 4
Really?
of my teeth fall off. I have
Really?
4 wiggly teeth.
How does that happen?
Okay, thank you, doctor.
You're welcome. That's nice. Okay, tomorrow you should tell me how did your teeth fall off? Or tell us.
See a doctor?
How did your teeth fall off?
My teeth fall off.
He asked me.
Later.
I feel
Tomorrow.
I'm good with my teeth fall off. And I had a lot of money. I got like $10. You give it to me. Huh?
Still almost on the edge. It's okay. What's that?
Hi,
Oh, Michael.
how's everybody?
Good. We have
Good.
2 more students in the class.
All right.
I meant the kids. Yeah, that's not.
Oh yeah.
Well, did you see all the new cases on campus?
No, what is it? Yeah, I would like to know. Yeah, what was the?
They updated it yesterday,
Uh-huh.
and
Is it bad?
it's pretty crazy actually. There's 9 on-campus students that live on campus, and then there's 20 off-campus students and 2 faculty.
Few faculty. Oh wow.
2.
How many? 2.
It says two faculty and staff, so there's 31 total.
Wow, that's a big increase from.
It's a massive
5
increase.
last.
From 6, well, it went from 3 to 6 to 31.
30 fun. Okay, this is not good.
Yeah.
I was a
That's
little.
pretty
Like
big
I was
increase.
following the Jackson County information, and that was looking more reasonable. Like it used to be 10 to 15 before the school reopened, and now it is 15 to 21. But when you concentrate it just to the campus alone, then you see the significant increase.
Mm-hmm.
Well, let's see what the university decides. Yeah.
Mm-hmm.
It might just switch over to complete online, which means that, but then we might be able to still survive. We managed it last semester, but still, yeah. Okay. I uploaded a homework 3 just an hour or 2 ago, and I made it due on Tuesdays. So I hope that's still possible. And these are due on D2L. Try to submit it on D2L. Sometimes you guys submit it on the email. It's really not inconvenient when half of you submit this way and half of you submit that way. So try to do it on D12. It's just easier for me. Okay. And then we have midterm 1. One week from today, right? There is a chance that this midterm might be take home. I do have a question in mind, but I have to make sure that everything goes correct. So as of now, I don't know, but be prepared that maybe it will be completely taken. Okay, what else? Yeah, there's also the question about if you have any questions, please feel free to meet me on Zoom. My office hours are I felt you guys don't know about it because one of you guys approached me in an email, and it's hard to reply on an email because it leads to most often miscommunication. I'm not very clear. You guys will make a misunderstanding and we'll exchange 5 emails and it will be all completely tangent to each other. So try not asking too detailed questions in the email, but office hours I think can work. People have been meeting me in for the office hours. So it is Monday, Tuesday, Wednesday, no Thursday, Friday, 3 to 4 p.m. You can meet me in my office or on Zoom. So what I do is I switch on exactly the same Zoom account and password, and I sit in the office. So if you come to the office, that's also perfectly fine. On Wednesday, I have some extra hours, and that is 11 to 1 also. So 11 a.m. to 1 p.m. So that should help.
Did you say 3 to 4 p.m.?
That's correct, 3 to 4 p.m. Is that it? Otherwise, just let me know, and since Zoom is available, pretty much it's possible to have it, but just give me some a notice before and don't say that at 9 o'clock in the night I want help and I have to be there. And it's possible, but avoid that. I mean, I would like to have some time for myself too, right? So, but in principle, possible if it's an emergency, but I don't see any emergency coming in homework submission, right? Okay, so in this context, I should say, in a homework associated with 520, there is something like this, I suppose. I don't remember now. I think it is this.
Excuse me, could you turn the camera, please?
Oh, that doesn't help. So, what you guys took quiet, or you guys just didn't realize that I was even writing?
Thank you.
Sorry. Okay. So again, going back, homework 3, midterm 1. That's just update office hours: Monday, Tuesday, Wednesday, Friday, 3 to 4 p.m. and Wednesday, 11 to 1 p.m. Okay. And I was telling that this is 520. Not this course. That is the problem 1 deals with the vector identity starting this way. Try replacing r hat with vector r over r. That's a hint you guys have. And remember that the only identities you need is times r is equal to 1 and gradient of magnitude of r is r hat. Right. Just be logical and pretend that this is a differential operator and just operate it. And you should work after that. Hopefully that's a solution. Okay. Anything else you can think of? missing some? 1, 2, 3, 4, 5. Yes. Oh, Moses. Yeah. Okay. Okay. So let's keep going. This is curvilinear coordinates, but now we slightly went into differential geometry, right? We're talking about how unit vectors change in a coordinate system, let's say. So let's call this differential geometry, like a very simple differential geometry. We're not doing any complicated geometries. Like if it's a real space and time, and if you don't have orthogonal systems, then it gets more richer. Here we're mostly working with orthogonal systems, but at the same time we don't restrict. We haven't made that assumption yet, but most of the examples we're considering is orthogonal in the sense cylindrical and spherical. That's because we are just the first course in this way. Okay, so we said there are two coordinates. Let's say these are xi, like I is equal to 1, 2, 3. So that represents x1, x2, x3. Doesn't really have to be 3 dimensions, in principle n dimensions. And we said if so, this is rectangular coordinates, and this could be ui, u1, u2, u3. Example could be spherical polar coordinates where it is r, theta, and phi. If we have two such coordinates, we can define our basis vectors of one with respect to the other, and they there. So this is the covariant basis vectors. We said was E subscript I. That's equal to, how does the position vector, right? Position vector change with these coordinates. And we had a geometrical picture of this. Think of it as family of surfaces. How does it change with respect to certain basis? Yeah, so in the same context, we also said what are scale factors. That's all. So what are scale factors? It's hi, it's magnitude of the covariant basis vector. And what else? We also define what is called a line element. And all this with the idea that coordinates are central and rest everything is derived out of that. But you can change the whole argument and say that a line element is the central quantity and everything else comes out of it. Or the metric is the central quantity and everything else comes out of it. So line element is dr is equal to du I or over I, so that's just a property of partial derivatives, but then we use the idea that this is nothing but ui times, that's it. That's 3 quantities in the context of covariant basis. Then we have contravariant basis vectors, sort of the dual property in a sense, and it is equivalent to saying it's like rays and or surfaces have a unique set of normal vectors, right? So that's the connection between the two, and using that we can define another set of basis vectors, which is a gradient of u of I. In this, should I do that? So let's do a small exercise right while we are talking about contravariant basis vectors. Small exercise. So if we have a contravariant basis vector, we can multiply. This is rewriting whatever I have here. Now let me multiply this by a complete set, basically an identity. But completeness requires that this identity can be represented in terms of its basis set, and that is the I. It cannot be I because I've used up I, so this is EK. Notice I haven't yet defined my completeness, that comes later, but so I'm using a property that we have already considered in the last lecture. So that's correct, but this tells us there's a consistency requirement here, right? So this is a vector or a vector written in terms of a basis EK, but it's the same vector on both sides. It's like saying if you want to write I hat in terms of ijk's, it better be I hat here. So if you say that, oh, I want to write I hat in terms of A times I hat plus B times J hat plus C times A hat, it's obvious that A has to be equal to 1, B has to be equal to 0, C has to be equal to 0. Similarly, if you want to write one basis in terms of the same basis, then this better be an identity. This better be identity there. So that for consistency requires that EK started with avoidance times UI has to be LKI. Otherwise, you'll be writing one vector is equal to another vector. What does this mean? When can you have this k times I? That means that so this the implication is that this gradient has to be equal to d by duk. This is an implication or a suggestion, let's say. It's not a proof in the sense that might be small. Like if all these things fail when this there's a if it's not well-defined functions, if this coordinates are not well-defined. So right at the initial point, we are saying that all these coordinates are well-defined in the sense that each point in space can be truly represented in terms of these coordinates. So this gives you d by duk. That means that if we go back and write our gradient, so this means go back. That is fine. Yeah, go back here. So gradient is equal to E of k dotted with complete. So this is E of k dotted with del, and that means that this is E of k times d by duk. We will be needing this. Let's do an example. That's a cylindrical coordinates. We know E of k in cylindrical coordinates. It is E of 1 is rho hat. E of 2 is phi hat over rho. If it was subscript, it will be multiplied by rho hat. And E of 3 is z hat. So that means that my gradient operator in cylindrical coordinates would be equal to row hat times d by d row plus E2 is phi hat times 1 over rho d by d phi plus z hat d by dz, which is what we always use, right? So this is just, I mean, we are already familiar with it. How about this extra credit? Repeat this for spherical coordinates. Use this idea to write, check out what is the contravariant basis vectors in spherical coordinates and use this formula to get the gradient operator in spherical polar coordinates. Okay, so that's contravariant basis vectors. A small note on that. We will need that when we are talking about connection today. But before we proceed, that is, once we have the two basis vectors, we have orthogonality, right, which says that the I dotted with the j, it could be either way, I downstairs, j upstairs, however you want to do it, but one should be upstairs and the other should be downstairs. One is contra and one is covariant, and this is delta ij. That's orthogonality. And completeness is sum over the indices, but you don't take the dot product. So that as here the dot product is between the explicit vectors. Here, in a sense, dot product, the summation is between I. So it's better to say it as summation, as we pointed out last time. And this is one. And we talked about transformation last time. This is a small diagram we made, and that was transformation of tensors. So the point is that the way we have been writing, there seems to be nothing special about these tensors. The way it has been motivated as of now, it seems like if you have a set of 3 objects, or a set of 9 objects, or a set of 27 objects, it seems like it's a tensor of rank 0, rank 1, rank 2, and rank 3, and so on. But that's not really correct. It is a tensor only if they transform like vectors. Like, for example, first you define a vector, like a position vector based on a transformation. And using that transformation, you build higher quantities. So there is a basic transformation that you begin with. And based on the transformation, you have a higher tensor. So you have to begin with a vector, and then a compound way of looking at it is what a tensor is. So it is not correct to say that any set of 3 objects is a tensor simply because it can be written like a matrix or anything. So that's one small point in. Okay, so let me keep this here and go to the next one. Okay, so now that we have our basis vectors, it's good to know how does the basis vectors change from one point to the next point. Like, for example, in cylindrical coordinates. Let's do a reminder. So cylindrical coordinates. Forget the z. Z is coming out of the board. Let's say that's your circle. And that's your row hat. And this is your phi hat. diagrammatically, that's what it is. Which is, so this coordinate here, so this point is described by rho and phi, and there's of course a z coming out. So this is the intersection of rho equal to a constant, phi equal to a constant, and z equal to a constant. Those are the three quantities in there, and this angle is phi. And one could ask, how does, so there are two vectors, so let me ask, how does rho change with rho itself? How does rho change with phi? And how does rho change with z? I might be interested in knowing that. Think of this vector rho and change your rho. So this is rho hat. If I were to increase this radius diagrammatically, how does it change? That's one question we are asking. Or else, if you want it more explicit, rho hat is nothing but cosine phi in the I direction plus sine phi in the j direction. You can show this, you can derive this, and this comes out to be minus sine phi in the I hat direction plus cosine phi in the j hat direction. Algebraically, it is very easy to see what this is equal to, but I will encourage you guys to look at it geometrically. So for example, this is rho hat. As you increase the radius of the sphere, how does rho hat change? That's what it means to say what is the derivative of rho with respect to rho hat. If I increase this rho a little, so that will be here, right? That's your new cylinder if you want. And how does rho hat change at that point? So if I were to ask you now, what is change in the unit vector rho hat with respect to the radius rho?
Zero.
It is 0, correct? Is that clear across the internet diagrammatically? No answers? Or are you guys muted? Oh, yeah, okay. Is that, so try to understand that or have a geometrical picture of why that is 0. In this, it is clear, right? That is no rho to begin with. So derivative of something that does not have that quantity has to be a 0. How about rho hat changing with respect to phi? So change in phi has to do with this, right? So this will be the change in phi. You make a small change, this rho hat becomes this. This is what you do when you're evaluating centripetal acceleration, right? In your Newtonian physics, if you were to ask how does the acceleration come out to be v square over r, if you were to derive that, actually the direction and the magnitude, then you will do this geometry, and then you will say that, this is your position, change in phi, that's your velocity. So velocity is in the phi hat direction, correct? So rho hat, or algebraically saying this will, when you differentiate this, this will become phi hat. Right? So this becomes phi hat. And what about rho hat with respect to z? Again, this is a unit vector. As you come out of the board, it does not change. So that's 0. Do that quantity again. So now let's talk about phi hat. And what is d by d rho? D by d phi of phi hat and d by d z of z hat. Right. Again, phi hat, as you change outward, if you change the radius of the cylinder, that does not change. With respect to phi, it changes. That's actually the centripetal acceleration, right? If you change the velocity, it's only the direction that is changing. If it's only the direction that is changing, then the centripetal acceleration is inward. The same idea here, change in phi, you can show that it will be inward. So this will come out to be minus rho hat try to get this geometrically. It's a nice exercise. In fact, you can derive this pure geometrically. Oh, we have Moses. You're wondering what happened to you.
Yeah, sorry I'm late, guys.
No. Fine. Okay. So this is phi, and this is 0. And do the same thing, right? D by dz of, oh no, d by d rho, right? That's the pattern we are writing. So d by d rho of z hat, d by d phi of z hat, d by dz of z hat. And z hat is ijk, kind of rectangular coordinate. It doesn't change everywhere it is. That's it. So this is what we mean by how the basis vectors are changing with coordinates. In principle, you have all of it here like this, but we want to make a more general statement. Can we build a quantity which actually has all this information in one piece? Right? It's like saying if we have a metric, there's some information there about how do you measure distances at each coordinate. So we want to define such a thing, and that's what will be called a connection. This is very general now. So that's connection, and what we want to define is basically what we have here is unit vectors and the coordinates, right? And coordinates, apparent when you differentiate it with respect to the coordinates, that's equivalent to having a gradient, right? So we want to talk about the gradient operator acting on the covariant basis vectors. Okay, so that's the idea of a connection. Basically, whatever this chart is, what it is pretty much. But these are all vectors, right? This is a vector giving you, like this is very clear, vector giving you back a vector. So that's a vector equation. But it's nice, and this is also a tensor in principle, one vector, second vector, and there is an index. So it's basically a third rank tensor here. But it's nice if we can talk about components, like take the left hand side, what is a component in the phi direction, what is a component in the rho direction, and so on. So talk about components instead of the vector itself. So what do we do for that is whenever we want to take a component, we just multiply it with, so for example, if you have a vector A, if I'm interested in finding out what's a component in the direction of I, so I just multiply it with the unit vector there. So I don't talk about this. This is my quantity of interest, but I want to build components. So this is dotted with E of K. So I have got rid of this vector information, but I've introduced a K index. You don't gain much, but at least now we can talk in terms of ijk's. But there is a quantity from the left also, right? So there's a vector here, and an index there. So I got rid of this vector information by multiplying or contracting it with another vector or dotting with another vector. Let me define this to be, so this will be what is called a connection, and this is one vector still remaining. So it will be defined as A. And there are two indices to that. So that's I and K. And the position matters, I is the side and K, so this is shifted element. So again, there is a vector, this is a vector, but now it has nine components, right? I and K can take 9 values. So 9 components, a vector built out of 9 components. But now one should be careful here. So I use the word vector, but I'm being sloppy there. Remember what was my definition of a vector is anything that transforms like a position vector. And it turns out that this does not transform like a position vector. So this is not a vector. So that's why you just call it a connection. If it was a vector, you would say connection vector, or it's not a tensor at all. Okay? So note, we won't dwell into it too much. If you ever do anything related to this, this plays a very important role. It's almost like a gauge, if you want. So this is like, I should say, this is not a tensor. So let me caution, right? Not a tensor. It won't play a big role in our analysis because I'm just introducing the concept and I'll do some examples, and that is all that I'm going to do. I'm not going to build a theory based on this. But if you are doing general relativity, or even if you're doing quantum mechanics, actually, yeah, quantum information, like some of you guys might be working with Dr. Bird. He works on Berry space. So there is, you make a point or a sphere and you build things on it, and you define a connection usually on it, and that won't be a tensor. So be careful about that. If you're transforming things, be careful about that. But usually it is taken care of. It's very well-known factor. But as a beginner, I'm pointing you guys, but we will not need it very much. Okay, so that's your connection. But again, as I said, this is there's still a vector nature, or what I mean is this arrow nature in there, right? I want everything in terms of components. So as well multiply this also with respect to another basis vector from the left, right? So let me also, so this is now what will be called Christoffel symbols. Christoffel symbols. These are basically, if you take the dot product of this from the left hand side also. We started with this quantity, multiplied from the left, multiplied from the right, multiplied from the left also. So we will say Christoffel symbols will be, I'll write it here. First, let me begin with what I'm doing, what I proposed I'll be doing. So this is J dotted with A, I, K, which is the same as E, J, dotted with this vector from the vector nature, the gradient operator from the left. And let's stop the bracket. That's decently complicated structure in there. A lot of things happening. This is dotted with this. This is dotted with this, and ij is coming up. So try to have a picture of that, and this will be defined as our Christoffel symbol, and that has a notation. This is K on top, I and J. The relative position of K with respect to Ij doesn't matter. Okay, so so again, Ij will be a paired index. There is a symmetry in there, and that is K, which is separate. So it doesn't matter whether you write K this side, that side, or right on top. It doesn't actually matter. So this is an independent quantity, and we will try not to move this K to the bottom subscript, because then there is a confusion as to is it K or J or I, which one it was. So there is a small ambiguity if you bring the K down. So you'll always try to keep it upstairs. If we have to bring it downstairs, then one of the indices downstairs, then we will introduce a new notation, as you will see. This is a complicated quantity that has all this. This is basically a way of encoding this chart. Right? Notice each one is a vector on the right hand side. So this seems to be 9 pieces, but each one is a vector. So there are 3 components on each side, each of this. So 9 into 3, 27 components, and this has 27 components, 3 each, right? So that's 27 components, and that is exactly the right hand side of whatever we wrote. But since it's a vector equation, each equation has 3 pieces. That's what that symbol represent. It tells us how does this vectors change with as you move around. It seems like a very simple concept. We do that in cylindrical coordinate all the time, spherical coordinates all the time, but it has very counterintuitive concepts related to that. For example, you can ask, if you start from this point and go around in a circle and come back, you could ask, do these vectors come back to the same place? Does the basis vector come back to itself when you make a rotation around in the space? For example, I go around like this. So I start from here, and at each point I have a phi, right? So this is so think of this as my cylindrical coordinate. So this is my cylindrical coordinates. At each point I have my phi. Right? This is my phi hat. Go this way, that's my phi hat. And I keep going this way, I keep moving my phi hat, and the question is, when I come back here, does the unit vectors come back to itself? And counterintuitively, it turns out not always. There are situations and there are coordinate systems when this doesn't happen. And that's what leads to the counterintuitive thoughts. And when physical quantities depend on that, that becomes very, it gives you new things usually. Right? And again, at this point, maybe that's what I have an idea of making a question on this and maybe making an exam question out of it, but I'm not sure how much I'll be able to really succeed in that. So we will see how it goes. So anyway, so as far as we are concerned, Christoffel symbols are encoding this, and let's see what we can do. So our goal will be to actually derive this, find all these components. For what I will do here is cylindrical coordinates. That's slightly simpler. You will do this for spherical coordinates. Your homework is about evaluating this, each piece. There are 27 pieces. You'll have to do this for spherical coordinates. It's a little laborious work, mechanical, but it's a good exercise to do it. It'll give you a feel of what people do in general relativity. Right? There are lots of components here. This is only the Christoffel symbol. The curvature has one more index in it. So 81, so this is 21, so that will be 81, but that is three-dimensional. They work in 3 plus 1 dimension, so it is 4 raised to 4 components you have to evaluate. And each one is at least, if you're in a new space, if you don't have any data book to look at, you have to actually evaluate that mechanically, but you will notice that it's just a matter of bookkeeping. Once you do it, it's that. But it has information, especially this direction is important. In what direction, right? Derivative with rho. Notice that cylindrical coordinates, everything happens in phi, right? This is the important piece. Like whenever you're changing with angle, right, cylindrical coordinates does funny things. Right? Otherwise, it's all 0. If you go in the rho direction, it is nice. Z direction, it is nice. When it is in the phi direction, it does non-trivial things. And these pieces contribute, and we know how to deal with it. Most of the times, this is captured in the standard ways that we do. Okay, so let me develop some properties of Christoffel symbol, and let's begin by looking at so Christoffel symbols were based on this bracket or quantity in the parenthesis, right? So let me go back and look at what is gradient of E of I. What is that quantity equal to? We did a small exercise in the beginning where I said that I can multiply by 1 on the left hand side. Right, and this will be dotted with L times EI. Same idea. So So this will be E of K dotted with gradient operator, and we have di. This we said was d by du k.
So I have a question
Yes.
really quick.
Question. Yeah, go ahead.
So I'm following the patterns, but I'm not really following the meaning of a lot of this stuff. I don't know if that's just me, but
No, it is possible because usually everyone struggles with this when it is first time introduced. Okay, ask me. So your question is, you see the pattern, but you don't understand the meaning of what's going on. Is that what
right.
you
Like
said?
I feel like I could regurgitate an answer if you gave me something because you've given me patterns to follow, but I'm not sure I'm actually following exactly what's happening.
That's because I haven't introduced a physical topic yet. If you want, the way I'm only saying is that how does unit vectors change with coordinate points? If I move from one point to the next, how do unit or basis vectors change? And I would like to encode that information. That's a lot of information there because there are 3 unit vectors. I can change it in 3 different ways. So that's already 9 vectors, and each one will have 3 components. So that's 27 components. But I want to put that all in one piece, right? So this is a quantity that has all the information about how the basis vectors change if you move from one coordinate to a neighboring coordinate. Does that help?
It helps me. Like I get that part of it, but whenever you write down the Christoffel symbol and then I were to just look at it, I'm not sure I would see,
It's not, I don't expect you to see this and say that, I don't think you need a lot of experience, let's put it that way. Like, because this is abstract at this stage, right? I haven't told you which space I am in, right? Usually what happens is that this is very general. People work in one particular space. Let's say spherical coordinates, that's the simplest space you can think of. If you are in general relativity, you would work in, let's say, Schwarzschild metric. That's the name of a space. You don't have to be knowing about that. But there you will have an intuition for it. If you work on it again and again, then you have an intuition for it. But just by looking at it, can I say something? That's very rare. You have to be really working on it for a long time to have a good intuition. So currently, yeah, you're right that this is very mechanical, but I'm trying to give you a motivation saying that, okay, this is a piece that is an example. This is the kind of information that's there. But unless you evaluate this, you won't know. If this is 0, it is okay, good. There is nothing remarkable in there. If it's not 0, if any of these 27 components is not 0, it has a curvature feature in it. Does that make sense? Or helps a little?
I think so.
Yeah. So, so the answer again is that, yeah, it's okay if this doesn't give you too much of a feel. So that's the reason for giving this example to begin with. If I didn't even give that example, that would be completely abstract and too many variables in there, understandable. Like if it helps you, yeah, if you throw this to me in front of me, even I will struggle. I've got to look at it for a long time to see what that means. Helps?
Yeah.
Okay. Yeah. So hopefully, maybe as you do your homework where you will evaluate these symbols for spherical coordinates, maybe you will get a feel for it. I mean, it's like saying, why do we do multiplication tables in high or elementary school? Be repetitive, right? When you're studying it, often I'm sure everyone says that this is hopeless, there is no point in it. But then, as an instructor, I would say that in the future you will see that it is not convincing. So that's the same answer I can give here I don't know. Yeah, maybe. Yeah, it's not a good answer. Okay. With that, so now what I'm doing here is that I want to know some actually symmetry properties of the symbol. Like there is some symmetries in there. So what I'm trying to motivate is that so just basically evaluating this. I already did this part earlier before we began the connection part. And this is a vector. Now I multiply it with ek from the, let's say, ek or ek prime, right? Ek prime dotted with del times ei. That's part of the Christoffel symbol that's sitting there, right? This is only from the left side I have multiplied it. And that gives me ek prime dotted with k by uk. Using orthogonality, we know that this is k prime k, so that's the same as e by eu k prime times e of I, because this quantity here is del of k prime k. Is that okay? So a better way of writing this is ek dotted with del I, forget the primes, I replace the primes with k. This is actually, let me write it as j, since now I can change to any variable I want. E by uj of I. Like that connects with what we have here on the left side. But now I can use my definition of covariant vector. This is equal to d by duj, d by dui of position vector. If I notice that, then I use the idea of partial derivatives commuting, right? Whether I have I on this side or onto the right, it doesn't matter. Correct? So that implies, this implies that Ej dotted with the gradient operator acting on the ith covariant basis vector is the same as swap the I and j. Or if I were to write it in terms of this partial derivatives alone, like in this language, if I were to do this, what I'm saying is d by duj of ei is the same as d by di of ej. That's not always obvious, right? Whether that will work or not. So let's do a small example. Like we have the cylindrical coordinates here, right? So example. Right. So let's think of d by d phi. So j is equal to 2. And let's say So d by d phi of rho hat is there. So let's say this is I is equal to I is equal to 1. Correct? So that would mean d by d phi of E rho. That's the same as d by d phi of rho hat, which is phi hat. If I do the left hand side of this. But what if I do the right hand side of this? I would say this is d by I is 1 now, d by d rho. Right, d by d rho of j is 2, so this is E phi. It seems like, oh, how is this going to work? Because this is a rho, right? Radially things don't change usually. But let's see how that works. So this is d by d rho. E phi, if you remember, has a rho in it. Right? If you go back, this has a rho times phi hat. Right? Did we write that anywhere? No. Okay. Remember your cylindrical coordinates E rho is equal to rho hat. E phi is rho times phi hat, and E z is z hat. And if you have to do with the contravariant, this will be the same rho hat. E phi is phi hat over rho. This goes in the denominator, and E z is z hat. So we have been using this. I think, did we do this? So yeah, we did do this a couple of, but you didn't do it in the homework, so maybe it's not really familiar. And now you see that, of course, the phi vector doesn't change with radius, but there is this rho. When it hits that, that gives you just 1, right? So that's equal to phi hat. So it is indeed correct. Right? So this does work. But that's not very obvious. Like we are saying, in general, in any coordinate system, this works. That's it. It's not immediately trivial, but it's kind of a nice feature of the coordinate systems. What that means is that if you are doing Christoffel symbols, this is with J and I here, right? J and I on this left-hand side. What this implies is that Christoffel symbols Kij is exactly equal to Kji. So that reduces a lot of work. Right? Instead of actually doing 27 components, you have to do less than that. How much less? How much less? 6 maybe? Less? 6 less? Maybe you have to do only 21 maybe, right? That's my guess. Yeah. So there's this symmetry in there. So you have to do only 21 of them instead of 21. Small symmetry in there. So that's one property which again you can use in your homework. I asked you to calculate 27 components of the spherical coordinate, so you have to do only 21, and the rest of, like when you, for example, if you have evaluated gamma 1, 3, 2, immediately you know gamma 1, 2, 3. Right? So that way it's slightly easy. Okay. Any questions at this stage? Is this still too abstract? It is, I guess, except when it comes here, maybe.
Pretty abstract.
Pretty abstract, yeah. It is. But your homework, as you use the word, I pretty much asked you to mechanically calculate this You use the word what? I can't say that.
Regurgitate.
I cannot say it.
Say vomit.
Yeah, it is that, but try to see ask yourself questions like, why is this the same? Like, in a coordinate system, why would this be the same? And try to geometrically see that. That usually has a lot of insight. And if you are in a new thing, it might lead you to some interpretation of what you're doing. That's the best I can suggest. Okay, so what we have to do some more, a little bit more. Or actually, while we are doing this, I can actually come back and give you the full expression. The point is that the Christoffel symbols actually, instead of writing it in this manner, can actually be evaluated using the metric. But I won't reach there if I start with it. But let me do some examples so that you know how to do your homework. So let me evaluate some components. So notice our Christoffel symbols. This in full form, it looks like this. J dotted with gradient I dotted with K. That's too many basis vectors, but using the property we mentioned in the beginning of the class, this is nothing but E by EUJ of EI dotted with E of K. And this is the formula you should use for your homework, or that's what I propose. You can do it using the metric also, as I will show in the next class, or if you use the internet, most of the time people evaluate the Christoffel symbols using the metric, not using this formula, right? But I'm suggesting that you do your homework using this, but if you want, you can use the metric also, but I haven't taught you that yet. So let's do this in cylindrical coordinates, right? So let's do some example. Since it seems like this is too abstract, so doing an example and getting a feel for something that we already have an intuition for, that helps. Right? So what is cylindrical coordinates basis vectors? Let me first of all say that 1, 2, 3 means 1, 2, 3 means rho phi z. Right? That means the rho is 1, phi is 2, and z is 3. That's not very obvious. Sometimes you can also write it as 0, phi. And it's a personal choice, but so that's my notation there. And E1 or E rho is rho hat. E phi is rho times phi hat, and E z is z hat itself. E rho is equal to rho hat itself. E phi is equal to phi hat over rho. I wrote this before. Z is equal to z. So that's the two basis vectors.
Those are supposed to be contravariant, right?
Tell that again?
Aren't those that E5?
Oh, yeah, mistake. That's on the top, right? Mistake. Phi and Z. Thank you. And if you want, I can also add that rho hat is cosine phi I plus sine phi j, and phi hat is minus sine phi I plus cosine phi j. Right. And let's do, for example, gamma 1, 1, 1. Right. So there's 27 of them. We begin with gamma 1, 1, 1. That's the same as saying that this is in terms of rho phi z, this will be rho, 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 right? So this is the same as d by du1, e1 dotted with e1. Right? And that's the same as d by d rho, u1 is rho, right? E1 is e rho dotted with e rho contra. Substitute the quantities in here. So this is d by d rho of rho hat, and then dotted with rho hat. But we already said that the rho hat does not change with the radius, right? So this is 0. So that's equal to 0. So we showed that first component is 0. Right? And in your homework, you have to do this 27 of them. Right? It's a little laborious, I understand. But yeah, that's the learning part. Let's it is a non-zero one in this. Let me do a non-zero one. I think it is right here. Yeah, let's do gamma 1, 2, 2. So you organize all of them however you want to. If I were to do gamma 1, 2, 2, this comes out to be equal to gamma rho phi phi. That's d by d phi of e phi and dotted with e rho. So that's equal to d by, so let me explicitly write this again, d by d phi. E phi is rho times phi hat dotted with rho upstairs, that's rho hat. That's the same as the rho that comes out of the derivative. Dotted with rho hat. How does the phi hat change with phi itself? We said that was minus rho, right? So this is something went wrong.
Where did we say that was minus rho? I don't remember that.
Oh yeah, I didn't say that. Yeah, minus rho hat. Sorry, yeah. Okay, I was confused. Yeah. Okay. Since I said minus rho, then I started thinking, oh, that's wrong. Okay, minus rho hat. Correct. Thank you. So this is is that clear why it is minus rho hat? Or was that the question as to why it is that?
I don't know why it's minus rho hat.
Oh, because we set this here, right? I can do that again, but let's point that out here. So we set this here, right? This one?
Oh, okay. Okay.
Right, in that chart we said that was there. So again, visualize this. This is the reason why velocity is tangential when you're going in a circle, right? Like the change in position vector is, centripetal acceleration. So your velocity is in the tangential direction, but as you move, you're changing the angle. So the acceleration, which is the change in velocity, is in the negative radial direction. Right? That's the same idea. So think of it as centripetal acceleration. Helps?
Yes.
So that's minus rho hat. So that is minus rho times rho hat dotted with rho hat, which is minus rho. That's one non-zero quantity in that. And there will be a lot of zeros when you evaluate your results, by the way, just for your information. Let me do one more example. So let me do 2, 1, 2. Right. So that's equal to 5 rho 5. Notice that when you write ij here, it is the derivative is the jth component. It's the second piece that you take derivative with. So this is equal to d by d phi of e rho dotted with e phi. So make sure you translate that correctly. And then the same idea, d by d phi of e rho is rho hat dotted with e phi, which is phi hat over rho. The change in the radial vector with respect to angle is actually the tangential vector. So it is phi hat dotted with phi hat over rho. That's 1 over rho. And this will also be equal to, so now I don't have to do further. So this is 2, 1. This is also equal to 1 over rho, right? That's by symmetry. I say one small piece of calculation. In fact, it turns out that cylindrical coordinates, everything else is 0. Okay, these are the only, so only 3 Christoffel symbols are non-zero. Rest everything is 0 in cylindrical coordinates. And that is the case when you have a lot of symmetry, like spherical coordinates has a lot of symmetry. You will see a lot of zeros in there, but it's not as large as cylindrical coordinates. So in this case, it's only 3. There, I think it is 6 or 9 that survive, or actually 6, and then you use some symmetry to get another 3 out of it. So that will be your homework. And I will give you another expression for Christoffel symbols in terms of metric. That will be in the next class, and slightly talk about the curvature tensor, which will all hopefully be coming in your exam also. Otherwise, I'll make a class exam with small questions. So on Tuesday, I'll be able to tell you clearly what your exam will be about. That's all. Let me stop here. You have a few more minutes, but let me stop. So the number of cases is not a good news, huh? Not at all a good news.
Yeah, not good news. It's a pretty significant
What
increase.
is the number of cases?
32, I think.
Oh, Moses came a little later. So Jordan was saying that they updated the information on the website. The number of COVID cases have increased significantly inside the campus.
Yeah.
So be careful. Yeah, be safe.
It looks like, yeah, it's right here. There's 31 cases now on campus. Well, people that are enrolled at the university.
You know, it's sad to say that, but I think it's expected because I've been listening to Dr. Fauci, the head of the what do you call it? I don't know, but yeah, the disease center or something like that. It will be, I mean, expected since people are gathering together, and it kind of hits back. They call it the second wave or something like that, but it's sad to say it, but it's expected everywhere. I mean,
True. Yeah.
Well, if it triples, like it seems to be doing every week. There was 3 the first week, then 6 the second week.
That's an exponential thing, right? I mean, 3 people,
Yeah.
3 raised to 3
Yeah.
is 9 raised to 3 is 27. So that's the increase this week. Every week it's increasing that much.
I've heard that some instructors make the coronavirus cases like an exam question last spring. So,
Could be.
Well, hopefully it doesn't raise to the third floor this week.
yeah.
It would be a lot of people.
Yeah. God forbid.
I mean, even if next week, I mean, I can't imagine they're going to have to say something about even just this week. I would be surprised if they don't say something, give us some insight about what their plans are. Like if it continues with this trajectory, I cannot imagine them saying, yeah, you need to come to campus, because it's just a lot of people.
Yeah.
They need
So,
money.
excuse me, doctor. I mean, during the office hours, do we use the same link as the lectures to get?
Same link.
Good. Thank you.
Yeah, talking about the cases, I am also a little wrong there that I kind of encouraged you guys to come to the class, right? So I also contributed to maybe 0.1% or maybe 1%.
As long as your students don't have it, then you haven't contributed.
Yeah. Okay, good. So
Stay safe, guys.
But it's smart. It's like I have people that are around me, like 3 or 4 pretty high risk people that I'm around kind of often. So I got to be responsible about it for sure. Because it's probably not going to affect me. And if I get it, it's probably not that big a deal. But, if I have it and don't show symptoms and am a carrier and then spread it to some of those people I'm around, it's disingenuous for me to do such a thing, to be honest. So I need to be careful and make sure that I'm responsible as a healthy person.
Yeah. Same situation here, man. I live with my mother here, and she's 70, and I mean, I restrict my my gatherings, my encountering with people. I mean, just to make sure that I do not infect her. Because it's very dangerous to old people,
Sure. Yeah.
Probably won't affect us, but if we're only worried about ourselves, then it's probably not that big a deal. But yeah, so well, hopefully it doesn't get much worse. But the trend right now looks like it's trending up, at least on campus for sure. So
yeah.
I was just curious. I called the SIH, Family Health Clinic, to see if they had tests, and they said they'd run out. So they gave me another number to call, which I haven't called yet. But that just makes me wonder, like,
how people getting tested.
How prepared we are in terms of number of testing kits and stuff.
True.
Yeah, that's concerning. Very, very concerning.
Okay.
See what happens. If it goes all online, It worked out pretty well last semester, I felt like, in terms of, especially your classes. I felt like you did a really good job at
Less of, once that reaches that stage, I think then the classes are not the important thing.
than the
But
what?
plus, if we reach that stage that people are getting sick, especially someone in our class, then I think class is not the important part of it. Then we should always try to be safe first. But if all of us are good, in good health, then this can always go as we are doing.
Mhm.
Yeah.
But hopefully we all survive. Because all of us get sick at different times, it will disrupt. Especially if I get sick. Yeah, it surely did.
No,
I don't know how,
stay safe, please. Stay safe. Take
I
care.
don't know how disabling it is, but I assume that it'd be hard to keep the classes going. Let's see. Let's keep. It's hard to predict these things. Yeah. Let's do what we're doing. Yeah. Okay.
Take care, guys.
All right.
Bye, guys.
Take care.
Bye bye.
Bye.